Hello everyone, welcome to the sixth session of seafood canning technology. Through the previous sessions, we have already discussed the historical perspective of this technology, the basic concept of this technology, the container part, what are the different containers, then the process. So the basic CCPs we discussed. So in this session, we'll be dealing with the thermal process calculations. So, since the canning is a thermodynamic process, so different kinds of thermal calculations or mathematical calculations are required to flawlessly plan as well as execute the thermal processing preservation process. So, we also discussed that the success of any thermal processes or any canning technology is basically it is a time temperature combination. So depending upon the variety of the product, the type of the container that we are going to use, the type of the retort that we are going to use, and the severity of our processes. So depending on all these parameters, the type of the ingredients that we are going to pack within the containers. So depending on all these parameters, the time temperature combination is going to vary. So every processes should be meticulously planned and calculated without any kind of fault, because if you over calculate it or under calculate, these are the two possibilities. If you over calculate it, what happens is that the process is much more severe than necessary, and the product may be overcooked and it may lose the consumer acceptability as well as the nutritional properties. So if you under calculate, what happens is that the severity of the process may not be sufficient enough to eliminate the reference microorganism or our target microorganisms such as Clostridium botulinum. So this is the issue. So the calculation must be perfectly, or it must be as accurate as possible. So there are different kinds of calculation methods, thermodynamic concepts that has been developed over the period of years by different scientists. So these calculation processes can be perfected over the time. If you take a bacterial population, how a bacterial population grows in a system. So the growth curve of bacteria can be classified into different phases. So initially there is going to be a lag phase, and another important phase is exponential growth phase is there. Then there is a stationary phase, and then there is a death phase. So this is like a normal or general standard growth phase or growth curve of a microbial population looks like. And also it has been also proven that the increase or decrease in the number of microorganisms in a given standard environment is in a logarithmic scale. So they follow a log scale of either multiplication or reduction in a particularly given environment. So if we take this growth curve of microorganisms, so in the case of thermal process calculations, what we are interested in the death phase, because we our idea is to bring down the initial number of microbial population up to a definite level or a predetermined level as soon as possible or within the stipulated time. So that is our idea. So in generally for developing thermal process calculations, we take a number of bacterial cells in a log scale against time, and from that growth curve we remove other stages. Other stages means the lag phase, exponential phase, and stationary phase, and then we consider the death phase alone. So then if you take only the death phase, the thermal death curve of a microbial population can be drawn. Since the reduction is in a logarithmic scale, one axis we will get the log values of bacterial population, the reduction of the bacterial population, and one axis we will take the time minutes of heating at that particular temperature. So that reduction we will get a logarithmic scale reduction or a straight line of reduction. If you closely observe this thermal death curve or this kind of logarithmic scale reduction, different kinds of information can be obtained by observing from this graph. So, like from this graph, various information is that the time information we are going to get. The logarithmic curve is also we are going to go, and logarithmic scale can also be converted into arithmetic curve. So arithmetic curve usually will not be on a straight line. To get a straight line only, we are converting the arithmetic data into a log scale data, so that we will get a straight line. So from this information, different kinds of thermal properties of or thermal characteristic of various microbial organisms can be drawn. It may be called as thermal properties of microbial destruction. So this microbial destruction or this logarithmic scale based reduction of microorganisms actually signifies different kinds of properties. From this reduction curve or thermal death curve, we can derive different kinds of properties of the microorganism. So the curve itself is called as thermal death curve or TDT curve. And from this thermal death curve, we can draw values like d value or decimal reduction rate value. And also another curve can be drawn which is known as thermal resistance curve. And from the thermal resistance curve, we can draw values like Z value. Then like F values and P values are also can be drawn at various stages. Then the lethality rate is one another concept, and the Cook value. So these are various thermal properties or thermal reduction properties of microorganisms. And these are the different kinds of properties that we are going to derive from these various thermal reduction or thermal resistance curves that we are going to derive. So the initial the point or the property that we need to understand is that this is a thermal death time curve. So that is the initial curve or thermal reduction curve that we are going to draw. So the thermal death time curve or TDT curve is also known as survival curve, because it is not only the death, because even though there is a death of bacteria happening, but there is a certain number of bacteria who are surviving the period as well. So it is also known as a survival curve. And also, generally, another terminology for this particular curve is called a decimal reduction curve or DRT curve. So these are the three different terminologies for this particular kind of curve or death curve that we are going to draw. So basically, how we can define the thermal death time is basically the TDT or the thermal death time is the minimum time taken to kill a population of microbes at a specific temperature. So it is a minimum time taken. It's a time value. From the TDT curve, we can find out that the minimum time required to eliminate a particular given number of bacteria or given microbial population at a specific temperature. These are one of the important points that we need to remember. So there is going to be one log reductions. One log reduction means basically in each log reduction there is a 90% reduction that is happening. So that is one parameter, one point that we need to remember, because regarding the log reduction, what do you mean by log reduction? And why this is important means death curves of three species. So if you take different species of microorganisms, in this curve you can see that the death curves of three species of microorganism at a constant or particular temperature is given. From this you can see that rate of reduction is different in the case of different species. Depending upon the species wise, the d value or the decimal reduction time or the rate of reduction of a microorganism is different from different species. Why it is different means at a particular temperature the resistance of microorganism is different. Each microorganism have different heat resistance properties. So according to the heat resistant properties of each microorganisms, there the rate of reduction is going to vary. So what do you mean by d value or decimal reduction time? So there are certain characteristics of d value, because some properties of d value. The d value is basically you can define it as the time required for one log cycle reduction. That is one definition possible. And another definition is heating time in minutes at a constant temperature that will result in reducing the number of microorganisms by a factor of 10. That is one definition. And another definition is time for the survivor or the TDT curve to traverse one log cycle. And another definition is heating time at a constant temperature required to kill 90% of a given number of microorganisms. So these are different ways in which this particular d value can be defined. But the definition is maybe different, but it all indicates at a particular property. So from these all the definitions we can say one thing is that temperature is constant. All the definitions are speaking about the constant temperature, and all the definitions are speaking about change in time. So considering the d value has its own certain properties that will help you to define the d value or understand the d value much better. So first property of d value is d value remains the same for each log cycle. So how many log cycle reduction time you are calculating, the d value is going to be the same. So d value does not depend upon the initial number of microorganisms. That means whatever be the initial number of microorganisms, the rate at which the microorganism is going to be killed is going to be the same. And another property of d value is expressed in time units minutes. Like it is the d value unit of d value is minutes, and 90% reduction in one log cycle. That we have already discussed that one log reduction is basically 90% reduction in the given number of microorganisms. So these are the properties of d value. So d value is usually written as T is usually written as superscript. So there is a T. T means reference temperature is always written as a subscript representing d value. So for example, d value at 100 degrees Celsius is written as D100, where 100 is written as a subscript. So again, if you are considering this thermal death time curve, one log reduction, if you take one log reduction, that is from 10,000 to 1,000, which is a 90% reduction, or one log reduction, a multiple of 10. So if you take one log reduction in a particular axis, you can see that the time change or the increase in time required to bring that one log reduction. So that is basically, and if you take that one log reduction into a single log reduction into a graph, and if you magnify that area, you can find out that it is a one log reduction. That is 10 raised to 5 to 10 raised to 4, the one log reduction of microorganisms. So if you take the initial number of microorganisms as log A and the final number of microorganisms as log B, and if you take change in time as delta T, delta means delta signifies a range of data. So if the change in or increase in temperature to 5 minutes to 10, so within 5 minutes to 10 minutes, that is time in minutes, around one log reduction has happened. That the change of time is taken as delta T. So from this we can actually derive an equation from that logarithmic reduction graph. So we can write it as the d value or dt is equal to delta T divided by log A minus log B, where delta T is the change in temperature in minutes, and log A is the initial number of survivors, and log B is the final number of survivors. From this equation, you can cross multiply it, and we can also find out the time required for, if the d value is already known, we can find out the delta T value or the time required for that particular d value. Then delta T is equal to d value into log A minus log B. So using this equation, we can find actually two values: the change in time, the time required for bringing down a logarithmic scale reduction, or the d value of that microorganism if it is heated for that particular time. All this happens in a constant temperature. That is what we need to keep in mind. So delta T, as already we explained, that it is the total exposure time. Log A is the initial population. Log B is the population size after the thermal treatment. The d value is also considered as temperature dependent. That we always state that thermal death time curve happens at a constant temperature. So d value decreases as the temperature increases. So there is a reciprocal relationship between d value and the temperature. Higher the temperature, the lower the d value, and the lower the temperature, higher the d value. So d value decreases as the temperature increases, and d value increases as the temperature decreases. So there is less time required to reduce the population by 1 log at higher temperature. So the time required to bring a 1 log reduction is different from a lower temperature to higher temperature. So from this graph, it is clear that there are 3 temperatures are taken at the same microorganism. So the log reduction happening, that you can clearly see that the time required for 1 log reduction is different in the case of 3 different species. The same bacteria, 3 different temperatures. So 120 degrees. So the higher the temperature, the time required is going to be reduced. So that proves that d value is temperature dependent. And also the d value is an index for sensitivity to thermal killing. So for example, we will take which one is more sensitive to heat killing or heat death, thermal death at 100 degrees Celsius. So two microorganisms are explained here, either Bacillus subtilis or E. coli. So 100 at 100 degree temperature. So it is an index of heat sensitivity of a microorganism. Here you can see the E. coli is at 100 degrees centigrade. The time required to reduce Bacillus population is longer than the required for E. coli. That means the Bacillus population is more heat resistant than E. coli population. We take decimal reduction time, we calculate the decimal reduction of different bacteria at a reference temperature. So d values of some of the microorganisms at 121.1 degrees Celsius is given here. So you can see that Geobacillus geothermophilus d values around 4 to 5 minutes. Clostridium thermosaccharolyticum is around 3 to 4 minutes. Clostridium nigricans, it is 2 to 3 minutes. Clostridium botulinum type A and B, 0.1 to 0.2 minutes. Clostridium sporogenus with PA3679 strain is 0.1 to 1.5. And Bacillus coagulans, it is 0.01 to 0.07 minutes. Here we consider an example. The problem is to calculate the d value for a bacterial suspension of 10 raised to 9 CFU per ml that was subjected to 85 degrees Celsius for 15 minutes, at which point its density was reduced to 10 raised to 6 CFU per ml. So there is a situation given here, a mathematical situation. So the information available is the delta T is 15 minutes, the time of heating is already given. Initial number of population is given, which is 10 raised to 9 CFU per ml. Final number of population is given, which is 10 raised to 6 CFU per ml. And the time temperature is also given, it is 85 degrees Celsius. So we need to find out the d value at 85 degrees Celsius. So using the equation, we can see that d is equal to delta t divided by log n1 minus log n2. Adding the known values, we can calculate the d value as 5 minutes. So d value of that particular microorganism at 85 degrees Celsius or d85 of that particular microorganism is going to be 5 minutes under these conditions. And also another example is the problem is the D90 value of a bacterium is 2 minutes. And if starting culture has turned to 8 CFU per ml, how long should this suspension be kept at 90 degrees Celsius to kill the entire population? Here, the information available is different. The same equation, but the information is different. So here what they have given is the initial number of population. N1 is given, which is 10 raised to 8 CFU per ml. N2 is given, which is 1 CFU per ml. And D value is already given, which is 2 minutes. So, and temperature is also given, which is 90 degrees Celsius. So, delta T, we need to find out the delta T means the period of heating. So, here using this formula, you can find out that delta T is found to be 16 minutes. Another curve or another thermal phenomenon that we can derive through a particular graph is known as thermal resistance curve. In thermal resistance curve, in one axis we give D value in minutes and another axis we will give temperature in degrees Celsius. The thermal resistance curve indicates the thermal resistance of a microorganism with reference to the temperature to which is exposed to it. So, thermal resistance curve, it is basically similar to D value, but D value deals with 1 log reduction, the time in minutes required for 1 log reduction in the number of microorganisms. But the thermal resistance curve deals with the reduction in the D value, 1 log reduction in the D value and the temperature change. It is the temperature and D value that is connected in the case of thermal resistance curve. And in the case of time thermal death time curve or TDT curve, it is the number of microorganisms and time in minutes that is going to be compared. So similarly, like D value from thermal resistance curve, we are going to find out Z value, which is also known as thermal resistance constant. So Z value describes the influence of temperature on decimal reduction time or D value. Z value is the increase in temperature necessary to cause a 90% reduction or 1 log reduction in D value. So, if you draw a thermal resistance curve, you can see that in one axis we have a 1 log reduction of D value that is considered, and there is a subsequent increase in temperature required to bring that D value that is also discussed. So, if you take this 1 log reduction into a graph, similarly in the case of D value, so we have log D1 that is initial D value and log D2 which is the final D value and delta capital T which is the change in temperature or increase in temperature. If you convert it into a formula, we can see that it is like Z is equal to Z value is equal to delta T divided by log D1 minus log D2. Here delta T indicates increase in temperature difference, and log D1 means initial D value, log D2 means final D value. So again using this formula, we can like an example for application of Z value. The problem is a food processing company produces canned meat. Prevention of Clostridium botulinum spores from growing is important. The D121 for botulinum spores is 0.2 minutes and the Z value is 10 degrees Celsius. The company wants to sterilize the canned food at 111 degrees Celsius. What should be the length of sterilization if they consider to kill 10 raised to 12 spores per can content? So we will take it is in a different way. So since every 10 degrees Celsius decrease in treatment causes a 10-fold increase in D value. So it is considered that every time there is a change or decrease in 10 degrees Celsius on the processing temperature, it causes a 10-fold increase in D value. So if you consider that D111 is there, so what happens is that it will bring down a 10-fold increase in the D value of Clostridium botulinum. So we already know that D value of Clostridium botulinum at 121 is around 0.2 minutes. So 0.2 into 10, that will give you 2 minutes. Using the equation that we have already given, you can find out that D111 is equal to delta T divided by log D12 into log 10 raised to 0. Log 10 raised to 12 minus log 10 raised to 0. So 10 raised to 0 is the final log that we require. So using this formula, you can find out that it is around delta T is around 24 minutes. So they should basically treat their product at 111 degrees centigrade for 24 minutes to bring down the population to 10 raised to 0. So complete destruction of population. This is different kinds of how we are going to apply these equations at different methods. So average value of D and Z for different kinds of microorganisms are shown here. So Clostridium botulinum, the D121 is 0.2 and Z value is 10. Geobasicin of zero thermophilus D121 is can be 2 to 4 minutes, and it is the Z value is around 6. So like that, different D values and Z values are assigned to different microorganisms. So you can see that both the thermal death time curve and thermal resistance curve are shown here simultaneously. So you can see that the TDT curve almost similar, but deals with two different values. One is with the D value or decimal reduction time, or one is as a Z value, which is the thermal resistance constant. And another concept that we need to discuss is that process lethality or lethality rate or LR value. So the lethality of a temperature with reference to the processing temperature, that is 121.1 degrees Celsius in the case of canning. So every temperature have its own lethality rate. So that is the concept. So LR at a particular temperature is the ratio of the microbial death rate at that temperature to the death rate at the lethal rate reference temperature. So the reference temperature, what is the death value, or what is the thermal resistance of that particular lethality of a particular temperature. So the maximum lethality rate is assigned to for our reference temperature, which is 121.1 degrees Celsius, and lethality value, lethal value assigned is 1. So every temperature which is going to be below 121 going to have a lethality rate less than 1. So that is the concept of lethality rate. So lethality rate is defined as 10 raised to T minus TR divided by Z, where 10 is the logarithmic scale, because all lethality is going to be measured in the logarithmic scale of reduction. So 10 is basically the logarithmic scale. T is going to be the temperature at which the lethality is calculated. TR is the lethal rate reference temperature, and Z is going to thermal resistance constant, which is 10 degrees Celsius in the case of Clostridium botulinum. So example, if we need to find out the lethality rate at 110 degrees Celsius, we will using this equation, LR is equal to 10 raised to 111 minus 121 divided by 10. So it is going to be 0.1. The lethality rate of at 110 degrees Celsius is going to be 0.1. So maximum LR value is given to be 1. LR value at 121 point is equal to 1. And also using this information, we can draw a lethality curve as well. The time in minutes is given in one axis, temperature is given in one axis, and also lethality rate in minutes is given in another axis. And another value that we need to be discussing is that F value or integrated lethality. So in food industry, a unit of lethality has been devised. It is not called as F value. F value can be defined as number of minutes required for the specified number of bacteria to get destroyed at a given temperature, which is almost TDT. So it is basically integrated D value. It can also be, because the unit and the concept is similar to D value, but it is the integrated effect, sum total of all the D values, all the lethality. So F value is usually mentioned as F raised to Z, and Z value as a superscript, and T temperature as a subscript. So indicates the time temperature combination of a process. The F value so indicates the time temperature combination of a process. And there is also another concept known as F0 value. It is also known as F0 value or F0 value. So it is the sterilization effect on the product which has been instantaneously heated to 121.1 degrees Celsius and held at 1 minute. So F0 value is a hypothetical value where the sterilization effect on the product, it is basically the sterilization effect on the product which has been instantaneously heated to 121.1 degrees Celsius and held at 1 minute. So F0 to calculate is basically it is delta T into 10 raised to T minus TR divided by Z, where delta T is the time of heating in minutes, T is the temperature of the product at the time interval, and TR is going to be the reference temperature, which is 121.1 degrees Celsius, and Z value is the temperature resistant constant, which is for Clostridium botulinum, which is 10 degrees Celsius. For example, time of sterilization is 15 minutes constantly at 121.1 degrees Celsius. So using this equation, we can find out that F0, if we are going to calculate the F value or F0 value of these organisms. Using this equation, we already know that F0 is equal to delta T into 10 raised to the lethality rate equation. So if you do the temperature, it is 15 minutes is already given. So F0 is equal to 15 into the time. Delta T is given 15 minutes and 10 raised to 121 minus 121. So same temperature. So what happens is 5 into 10 raised to 0. So 10 raised to 0 is 1, that as we know. So 15 into 1 means 15. So F0 is equal to 15. For example, another example, you can see that the time of sterilization is 15 minutes constantly at 111 degrees Celsius. What happens at the 11 degrees Celsius? So similarly contemplating, we can find out that 15 into 10 raised to minus 1. So 15 into 0.1, convert the log value, then it is 1.5 minutes. So F0 is equal to 1.5 minutes. So Clostridium botulinum, how we are going to depict the F value is that F raised to Z and Z value as the superscript and T value as a subscript. So F raised to 10 divided by 121.1, which is known as F0 value. So thermal death time of Clostridium botulinum is 2.52 minutes at 121.1 degrees Celsius. How will we find out the TDT value? So F0 is equal to 2.52 minutes. That is that the thermal death time of Clostridium botulinum at 121.1 degrees Celsius is 2.52 minutes. So F0 is basically 2.52 minutes. And how we can define the integrated lethality concept? So we already know that lethality rate is equation, which is basically it is an anti-log 10 raised to 10 T minus TR divided by Z, and F0 is delta T into 10 raised to T minus TR divided by Z, and delta T is basically time of heating in minutes. So F0 is the integrated lethality of all temperatures within the heating period. That is why 0 is known for. And for example, F6, if you say F6, the time interval for which the processing temperature has to be maintained at the core of the product to achieve the desirable lethality, which is the 6 minutes. That is why what is the difference between F0 value and F6 value, or any other value that comes as a subscript.
Thank you.